So up till now we've been looking at simple parameters like a mean and a standard deviation and looked at their distributions. Now we're going to look at ordinary least squares, OLS, and we're going to see that the parameters there, like the constant and the slope of an OLS equation, also have distributions. In order to do that, we're first going to generate our own data. So that's a very important topic to learn, how you can generate your own data to test the models that you're trying to estimate. So again, we're going to have a variable number of simulations, and we're going to again set it equal to 10,000. There's going to be a sample size, and this time let's set it to 20. I'm going to deviate a bit from the notebook, just to give you a different view on things, different way you can do things. But once you've seen this video, you should be able to figure out what we're doing in the notebook as well. So I'm going to specify a slope of our OLS equation of minus 0.2. So we're going to generate the data with a slope of minus 0.2, and we're going to see whether when we estimate this with OLS, we're going to see this minus 2.0 back again. So let's first look at our simulated x variables. So simulated x is equal to, again we're going to use TensorFlow, first random. And now instead of the uniform distribution, we're going to use the normal distribution. And as before, we're going to generate number of simulations, so 10,000 rows. And we're going to have sample size, so in this case 20 columns. So when you look at simulated x, you can look at the shape of this variable. And you see that this variable has 10,000 rows, so we're going to replicate our experiment 10,000 times. And each row has 20 observations, so we draw 20 samples out of the normal distribution. In this case it's the standard normal distribution, so the mean is 0 and the standard deviation is 1. I'm going to show you in a second how you can change this. So we have generated 10,000 different data sets, so the observations for x in our data set, and there are 20 of these observations. So this is part of the data for x. So now we're going to look at how we're going to generate our y variable. So we're going to say the simulated y is going to be equal to the slope that we specified. Yeah, so I don't have a constant here. There is a constant in the notebook, but I think you can figure out how that works. So we have the slope times simulated x. And of course we have to add some noise, so like the e or the epsilon when you write down OLS equation. And we're going to say that the noise is again, random. That is going to be normal. Number of simulations, sample size. Yeah, so if you do it like this, we have a standard normal distribution. But we may be interested in specifying a different mean or a different standard deviation. So let's quickly look how this goes. So in the Jupyter notebook, you do this with a question mark after the random normal. So we can specify a different mean if we want to, and a standard deviation. So the mean is specified using the word mean, and the standard deviation is specified using std_def. Yeah, so we're going to use that. So in this case, we're going to have random noise with a mean equal to 0 and a standard deviation equal to 0.5. And again, we're interested in the shape of the variable that we just generated. Yeah, so each observation of y is going to be equal to the slope times the observation of x. And added to this a noise term, where the noise is a normal distribution with mean 0 and a standard deviation of 0.5. My x variable is of the form 10,000 rows, 20 columns, and indeed my y variable has exactly the same form. So what we're going to do next is, for 20 observations, you could plot that as a scatter plot. We can estimate what the OLS equation would look like, so we can estimate the slope and the constant of that OLS equation. So for each row, we're going to have one slope and one constant, and we're going to do this 10,000 times, giving us 10,000 slopes and 10,000 constants, and these again are distributions of the slope and the distribution of the constant, and these we can plot.